So you see, we talked about the I1 and the sorry, not I. This both are I2. We talked about this I1 and I2, and we assigned a physical meaning to I2, right? But the thing is, we are really talking about the change in flux through the curved cylinder, not only through these cross-sectional surfaces, but through the entire curved cylinder. Okay, so so in other words, the total flux through the curved cylinder which curved cylinder? Well, this one, right? I mean, this curved cylinder, it includes, it has two pieces, so to speak, flux through top and bottom surfaces, which is what we have been talking about so far, and also flux through the side surface. In other words, the side surface, this thing, this stuff, not this, not the cross sectional. Let the side surface be called sigma. Okay, so therefore, I can symbolically write it as I can symbolically write it as B dot ds S t plus delta t, right, minus, well, it's really, I am not writing explicitly r and t and everything here. It would be here it would be r t plus delta t, here it would be simply r and t, but so therefore I am keeping this a little less just to avoid too much complication. So the difference in flux through the top and bottom surfaces plus whatever flux is passing through the side surface, okay, through this side surface, through this surface here, the side surface of the cylinder, right? And now these are all a B dot ds kind of thing, isn't it? Now this is all a B dot ds, and by the divergence theorem we get the integral of B dot ds is simply we know that this is equal to the integral of divergence of B, right, dV, and we know that this is equal to 0, always equal to 0. Divergence of B is always equal to 0 no matter what, right. So this has to be equal to 0. So this connection between the surface integral and the volume integral like this is through the divergence theorem. Okay, so there's that. So this is one important thing. Now let us talk a little bit about this guy. We have mostly been concentrating our attention on this fellow and that fellow. Now let's concentrate our attention on the flux through the side surface. So what is it? Right. So first of all, what is this sigma? The sigma is the side surface of the cylinder, isn't it? So sigma comprises length element along the loop. I will go back to the figure in a minute and show you what I mean. It comprises this, right, and of course this. Yeah. So it comprises the length element along the loop like I've written, and which is the v dt is essentially, so it would essentially be sort of a, you know, integral this times v dt, which is this. Okay. So so that's what I'm writing here. Okay. So over the side surface, this b dot ds is equal to the contour integral, okay, of b dot, what is this side surface? The side surface is the d small s, which is the length element, cross v delta t. Now it's important to figure out why I'm writing this cross, right? So essentially what I'm saying is it's a ds, it's a ds cross v. Well, the reason I'm writing this cross is because you see the v is along this direction and the ds is along this direction. So what would be the cross product of azimuthal times times a z directed field in cylindrical coordinates? It would be a radial, right? In cylindrical coordinates you have the radial, the azimuthal, and the z directed. So phi cross z gives you r, and so in some sense this ds cross this thing that we wrote down, ds cross v, this would be in the phi hat direction and this would be in the z hat direction, and the crossing these two gives you r hat, and that is exactly that is. So when we talk about the side surface of a cylinder, the outwardly directed area element is indeed along the radial direction. That's the reason we write this cross product, and this cross product is very, very important. Okay. This one I can also write as, I take the delta t outside, okay, and I can write this as a contour integral of v cross b dot ds. And this comes from vector algebra identity a dot b cross c, okay, and this is c cross a dot b, okay, and this delta t simply comes outside. You should try to figure out why this is true, okay, and this is a contour integral, right, of v cross b, and using the Stokes theorem the contour integral can be turned into a surface integral, and so I would have a curl here, curl of v cross b dot ds, okay, where this is a dot, okay, here, and there should be a dot here. The dot is outside of the bracket. Okay. So this comes from Stokes theorem, right, and so this equality comes from Stokes theorem. Okay. And you already start recognizing where this is an important part of the induction equation, right? Curl of v cross b, you recall how it appears in the induction equation. So therefore we have the third part now. So the I1, which we defined here, which is the change in flux due to the change in loop position, which we wrote down as this, yeah. So that is equal to change in loop position, right. So initially the loop was at st plus delta t, right, and the flux is right, dot d. You remember we are now fussing about I1 because I2 we have already gotten a nice physical interpretation of I2, so we don't worry too much about that. So let's now get back to I1, and so I1 is equal to this minus S of t B R plus delta t. You see, I am keeping the magnetic field the same. I am only changing the loop, the cross sectional area, which is changing because of the change in loop position. Okay, and this is equal to minus delta t curl of B cross B. Right? This comes from here, of course. This comes from here. Okay. It actually comes from here and here. So what we did was we identified that this is equal to this quantity. This B dot ds is equal to. So that's what we did, right? And I1 we wrote it down like this, and so this is where we have this important thing, yeah. And we know that I2 is equal to, we had already written this down, this is equal to delta t S dB dt dot ds. We had already identified the I2 to be this. So essentially this becomes I1 and this becomes I2, and I1 plus I2 is what we are concerned with, of course, right. So therefore delta phi, which is what at the end of the day we are concerned with delta phi, and we wrote down delta phi as I1 plus I2, right, is equal to delta t times, because we identified I1 as curl of V cross B times delta t, we write down this as delta t times minus, this is I1, curl of V cross B. This is done, yeah. And I2 we wrote down as the same delta t dB dt, right, okay. And so plus like this, and of course I always have a surface integral, so I should have a surface integral here too, and what is this? This is what we started with for an ideal, if you recall, this is what we started with. dB dt is equal to curl of V cross B, right. So I put a negative sign on this, yeah, and I take it over to the other side, right, and so dB dt minus curl of V cross B has to be equal to 0, and that's exactly what we have here. We have dB dt minus curl of V cross B, and this is always equal to 0, right. And so since the integrand is equal to 0, the integral will always be equal to 0, and that therefore we have, right, we have this equal to 0. In other words, what we are saying here is that delta phi delta t, which in the limit goes to d phi dt is equal to 0, and this is what we were out to prove. Okay. So n phi is the magnetic flux, is the magnetic flux which is conserved with time, and this is a direct consequence of the induction equation. This is a direct consequence of the fact that the integrand here is equal to 0. In other words, this is the induction equation and this is in the integrand and it is equal to 0. So, there is no choice, the magnetic flux has no choice, it has to be conserved. Okay. So, what we have done now is we have shown how magnetic flux conservation or what's called flux freezing, and I want to put this flux freezing in arises out of the induction equation. This is what we have shown. And how did the induction equation arise? Well, the induction equation simply arose from Maxwell's equation with the assumption of infinite conductivity. Okay. And once you have infinite conductivity, you can never have an electric field inside the fluid, and so any electric field has to be only due to the fact that an observer is not inside the fluid at all. So, you have that curious E equals minus V cross B over C kind of thing, and you substitute that into Ampere's law and you get the induction equation. So, once you have the induction equation, which is, I would say, one could go so far as to say that this is a natural consequence of infinite conductivity, then we know that what we have shown here is magnetic flux is conserved. So, flux is frozen in a situation where the conductivity is infinite. Okay. Now, what about this? Why are we making such a big deal about it, right? So, the point is flux freezing, magnetic flux freezing is an important magnetic flux freezing is central to explaining dynamos, magnetic dynamos in astrophysical situations. So, the thing is, what's this thing called a dynamo? Well, a dynamo is, as you know, you want to sustain a magnetic field. That's what a dynamo does. And that's what you would do in a bicycle dynamo, for instance. These days you just have LED batteries and you turn the light on, when you want a light in front of a bicycle. But in the olden days, what you would have is you would have a dynamo that you would it would be a mechanical rotating object that you would tilt onto your bicycle tire, and so you would be mechanically rotating the spindle by your muscle power, and that would generate a current. Okay. Now, we know in MHD the current is nothing but the curl of the magnetic field. So, in our context, a dynamo would simply mean a device that helps us sustain magnetic fields. Okay. Now, why is this important? Because in astrophysics, magnetic fields are quite ubiquitous. They are everywhere. In many cases, they are measured directly, as in the solar wind, the immediate environment of the earth, and so on and so forth. We know that the earth has a magnetic field, and we have indirect evidence of the fact that the sun also has a magnetic field. Okay? And we have even more indirect evidence of the fact that the galaxy is permeated by a magnetic field. Fairly exotic objects like pulsars, they have very high, very strong magnetic fields. These are all indirect evidences, but nonetheless, magnetic fields are everywhere in astrophysics. This is kind of well known. But at the same time, no plasma is infinitely conducting, okay? And there's always a finite resistivity in any plasma. And as we know, this kind of so this integrand would never be exactly equal to 0. There will always be an additional term here, some kind of a lambda times a nabla square b, which would be a resistive term. So, essentially what we are trying to say is that in the presence of finite resistivity, magnetic fields simply cannot sustain. They will always decay away. And if you put in the numbers, you will find that for expected values of resistivity, really there is the magnetic fields that we observe have no right to be there. Okay? They should really have decayed away long ago. How are they there? That is the question at the heart of dynamos. Okay. So, the question we are asking is, what is the mechanism that generates how to. So, the question really that an astrophysical dynamo theory should address is how are magnetic fields generated or amplified from small seed fields. So, now here is the thing, you always have to assume that there was some existing seed field. The magnetic field that we are observing today is not that seed field. Okay? It's a very mature field, it's a tree, so to speak, that has grown from this seed, but you cannot get away from the fact you cannot generate a magnetic field from zero. You always need to have a small seed field. So, you have to, given picture, a given understanding of a magnetic field dynamo has first got to address this question, which is that how are magnetic fields generated or amplified from small seed fields. So, this is one question. Slightly more elaborate way of considering this question is you have to show that the presence of a small seed magnetic field renders a system of MHD equations unstable with time, so that you show and invoke an instability which make the seed fields, which makes the seed fields grow. So, this is one thing. This is one ingredient of bona fide dynamo theory. The other ingredient is that after the seed fields, have grown, how do they sustain themselves against resistive decay? Because now we are talking practical stuff, we are not talking an ideal MHD kind of situation, we are talking about a situation where there is always a resistive term, and that resistive term we have seen it leads to the decay of magnetic fields, decay with time. And so, if you wait for long enough, and in astrophysical situations it's always one can plug in the numbers and show that we have indeed waited for long enough in many situations. And if there was no mechanism for the seed fields, for the fields to have grown from the seeds and attained a certain value, if there was no mechanism for these fields to sustain themselves in some manner, then there was an instability which enabled these seed fields to grow. These grown fields would die due to resistive decay, unless there is a mechanism to sustain them. So this leads us to the next question that a dynamo scenario should address, which is that of sustaining. Okay, and so these are the two basic things about a magnetic dynamo. There are some other complications that sometimes, for instance, in the context of the sun, the large scale magnetic fields which have been generated, and somehow you can show that the large scale magnetic fields which have been generated are able to sustain. Okay, they are also cyclic. In other words, the large scale fields are cyclic in time. In other words, they grow, then they die, they grow again, and they die again. Okay, that's another complication. But So that's another complication, and we will not get so much into that. But you have to wonder now, why did I suddenly start talking about dynamos and so on and so forth? Evidently, it has some connection with the Alfven flux freezing theorem, right? So the most common approach to these two questions, to solving these two questions, how are magnetic fields generated or amplified from the small seed fields, and having amplified them, how do they sustain against magnetic decay? The most common approach is what's called a kinetic dynamo. Rather, this was historically the first kind of approach, where the velocity field V is specified, is prescribed or specified. I don't bother about how this came about. It's given to me from certain observations which we will discuss. Okay, and the magnetic field is evolved. The magnetic field is evolved in time, and we know very well. This is what we've been talking about for a long time now. What is the one equation that tells you how the magnetic field evolves in time in response to a given prescribed velocity field? The magnetic induction equation. You prescribe a certain velocity field, and then you see how the magnetic field is evolved. So this is at the heart. This is at the heart of this approach called a kinetic dynamo. Okay, and so what we will see when we meet next is that this particular approach has been quite successful in explaining at least some elements, not all elements. There are still very big unanswered questions in this field, but still there has been some remarkable success in explaining at least some elements of these two questions pertaining astrophysical dynamos. One is how do seed fields grow, and having grown, how do they sustain in the face of resistive decay? And we will mostly address the second question, how these large scale fields sustain using this kinetic dynamo picture. So we will discuss this when we meet next. Thank you.